Welcome to the Molecular Devices Automated Electrophysiology webinar series. This is our 16th webinar in the series. Today's speakers are Andrew Powell from GSK in the UK, talking about work that he's done on the Ironworks Barracuda system. And we also have Michael Donio from Europein in St. Louis, talking about some GABAA assays that they perform on the IronFlux HT system. I'm your host. I'm Jim Costanton. Been at Molecular Devices now for about 12 years. We have Jeffrey Weber, who will be handling the questions today with us as well. And I just wanted to give a very brief introduction to the instruments that we sell for ion channel drug discovery. So if we're look at the drug discovery funnel here, at the top of the funnel would be Flipper with fluorescent imaging plate reader, and then going down the funnel with very high throughput capabilities of the Ironworks Barracuda system, followed by two IronFlux systems that we sell, the IronFlux 16 or the IronFlux HT. And the IronFlux system covers a wide range of the funnel with the two different systems. The HT has about 4 times the throughput of the 16. And towards the bottom of the funnel, we have the Patch Express system and also our conventional electrophysiology equipment, the Axon electrophysiology product line. We are recording the webinar, and you can view previously recorded webinars on our website. Just simply navigate to the IronFlux or Barracuda web pages and click on the Resources tab to view webinars. And with that, I'll go ahead and turn the control over to our first speaker, Andy Powell from GSK. And let me go ahead and do that. And Andy, I'll let you know when your slides first come up. Okay, Andy, you have the control.
Just open my slides here. Okay, can you see those?
Yes, I can.
Okay, great. Okay, thanks, Jim. I should say up front that very little of the work was actually done by me, but done by members of my group and others over the course of the last few years. So the presentation focuses on our utilisation of the Ironworks Barracuda electrophysiology platform for ligand-gated compound profiling. So what I'll do, first of all, though, is I'll just touch on how we're using the Ironworks Barracuda for voltage-gated channels. We have presented some of this work at meetings before, so I won't dwell on that too much. But what I want to take you through really is some of our more recent experience at using the Barracuda for compound profiling assays for ligand-gated channels. Okay, so I'll very briefly start by just introducing the platform for those who aren't familiar. It's very similar in some aspects to the Ironworks Quattro, but obviously it's a development of that which gives you greater capability. So it's a mega ohm field platform. You can carry out either population patch clamp or single cell recordings. So population patch clamp are recordings from multiple cells within a well, whereas single cell is obviously one cell over the hole in each well. It has 384 electrodes and fluidic tips and 4 plenum electrodes. And it's really that array of 384 electrodes which has effectively increased the throughput by decreasing the amount of time it takes to read a 384 well patch plate. And because the electrode head and the fluidics heads can sit in the well simultaneously, you can carry out simultaneous ligand addition and recordings. And obviously that opens up possibilities for ligand-gated ion channels. You can carry out multiple compound additions, up to 10 compound additions per experiment. And what that's enabled is cumulative dose response curves within the same well, which is another way we've increased throughput. and you can also run more complex voltage protocols in the Ironworks Quattro. So our experiment run times are down for voltage-gated channels, and also because we can do these cumulative dose-response curves within a well for some channels, that's also decreased the cost per data point for what we call through-plate mode for some of our assays. Okay, so just to explain that distinction between the Quattro and the Barracuda with respect to the servicing of the wells by the fluidics head and the electrode head. So what happens with the Ironworks Quattro is you would have your cells at the bottom of the plate. The clamp would have been set up, the cell seal obtained, then the electrode head would move out of the way, the fluidic tip would come in, pipette in your compound or your ligand, and then it would have to move back out of the way for the electrode to come in and carry out the recording. So basically you have discontinuous fluid addition and voltage clamp recordings. The Ironworks Barracuda, however, has the well as pictured here, so the cells sitting underneath the fluidics, the position where the fluidics tip goes in, and these are now disposable plastic tips, and the electrode sits in another part of the well, so both can be there at the same time. Okay, this picture just shows the output of a 384 well Barracuda patch plate experiment, and what we have basically is this is a voltage gated channel, the L-type calcium channel. We have in column 6 a no compound control. In column 18 we have our high compound control where we see complete block, and what we have in the columns is 4 blocks of 5-point dose responses across the plate. So going down the plate, each one is a different dose response curve for a different compound, and we've got 4 blocks of 5 going across. As with the Ironworks Quattro, we use filters to remove wells which don't meet our quality metrics, so anything with lower seal resistances in population patch clamp is excluded, and we also exclude poorly clamped cells, any wells which have failed the whole test due to blocks or to air bubbles. But to be fair, that's not a lot of wells within the system, within each experiment usually. Okay, so I'll just touch on what we've done with voltage-gated channels and use the Herg channel assay that we're running as an example. So we've been running a panel of cardiac ion channel assays on our Ironworks Quattro for some time now, really to enable the early identification of compounds with any likely cardiac safety issues. And we do that at both at the kind of hit validation stage following a HTS for a program, and throughout lead optimization and, of course, pre-candidate. Once we've identified what we believe are clean compounds and we're moving towards candidates, then we will carry out gigaohm seal electrophysiology on other platforms for those pre-candidate compounds just to confirm the data across this panel of assays. So here I just show some Herg Ironworks Barracuda data. So this is an example where we are using the through-plate mode. We've got 6-point dose response curves in a well, so we can carry out up to 117 triplicate IC50s per run, allowing for a couple of controls on every run. We're looking at the tail current and just assessing that and looking at the distribution of current across the wells in the plate. You can see we've got a reasonably tight distribution here, as shown in the histogram in the centre. So the mean peak current here is about 1.6 nanoamps, and that's pretty consistent in our assays. And then looking across to the dose responses on the right of the slide here, you can see how well the data we've generated in the 5-point dose response curve in the red for the Barracuda correlates to the data we got from 11-point curves on our Ironworks Quattro, and with some Q-patch and patch express data for the same compound. And obviously we've done this with more than one compound, and we get pretty good correlations throughout, really. We've also established, as I alluded to earlier, a CAV 1.2 L-type calcium channel assay and a KV 1.5 assay, and we're just progressing some assay development around the other channels that we routinely run in this profiling panel. But of course, what we lacked on in using the Ironworks Quattro was the ability to provide physiologically relevant EFIS data for some of the ligand-gated neuronal liability targets that we're interested in profiling at this early stage of drug discovery. Specifically here, the GABAA receptor and the nicotinic acetylcholine alpha-1 receptor. So we hope that the Barracuda would enable this. So before I go on to describe that work, I'll just acknowledge that we had previously been able to record GABAA currents from the Ironworks Quattros, and this work was work that we published, Emma Hollands et al. In 2009. And we could basically, for slow ligand-gated channels such as GABAA, we demonstrated that you could record the current on the Ironworks Quattro, but only after the peak current. So you could record the sustained current of a GABAA response, basically by adding the ligand, and once the fluidic head moved out of the way, coming back in with the E-head, clamping the cells, and then running a step protocol to 0 millivolts, and we basically run a control pre-ligand recording, and then an agonist post-ligand recording, subtract the two, and effectively get our ligand-mediated current from the cells, which would be commensurate with probably sort of about 40, I think it was around about 8 seconds after the ligand has been added. And this, we were able to generate some reasonable pharmacology data using tool compounds, both for agonists, antagonists, and positive modulator. And our agonist EC50 came out at about 1.6 micromoles. The literature agonist EC50s range from 10 to 30. So obviously there's a bit of a disconnect, but rank order potency of things of compounds seem to come out similar. And you can see on the dose response that you do get a quite spread of the data as you look at the wells in the order that the recordings were made after the addition of the ligand. Okay, so I'll just touch on then why we're interested in GABAA from a safety perspective. As I'm sure you will know, antagonists, agonists, and positive modulators all carry major neuronal liabilities, either sedation or can be proconvulsant. As I said, we wanted to develop an early safety profiling assay. GABA receptor channels are complex stoichiometry, so they're pentaheteromeric receptors, predominantly in the CNS, and you have 2 alpha, 2 beta, and 1 gamma subunit. And we use the system basically where we have generated Batman viruses for each of the 3 subunits, and then transducing them into CHO cells a day prior to our assay. So putting those cells then onto the Barracuda, we just did some very preliminary work looking at the tip height and the impact that has on the current kinetics. So we're using GABA here as the agonist, and you can see in green with a high tip height, you get quite a slow onset of activation. Medium tip height, you get a faster onset, and with the higher tip height, you get a more rapid activation. But also, there's a little bit of a addition artifact coming in, when the tips are closer to the cells. So for our experiments, we selected the median tip height. We showed that the tower of activation and desensitization looked pretty tight across different wells, so pretty consistent. And then what we did was looked at how the peak current, indicated by the green arrow here, correlated with the current 1 second post-addition and 2 seconds post-addition in red and blue, respectively, and just looked at the distribution of current. And what we saw was that the distribution of current for the peak here is fairly broad compared to the distribution after 2 seconds. So it does suggest to us that the addition isn't quite as fast onset as we would like, and we are getting a bit of heterogeneity in the peak. However, it's interesting that even though whatever that heterogeneity is, as you look at the sort of sustained current during the desensitized, the decay of the current, the data clusters tighter, and you can see at 2 seconds we've got a reasonably good distribution, though of course the currents are smaller, but still good. These are 1 nanoamp currents at this point. And of course what we wanted to make sure that across the wells there was a reasonably linear correlation between the peak and the current after 1 and 2 seconds, just to give an indication that the shape of the current was similar across those wells. And that's what's shown here, just in this plot, which correlates the peak current to the 1 and the 2 second current. Okay. So we went on to carry out some pharmacological evaluation of this, and starting off with a GABA dose response, and here this is 11-point data. We've basically here solely looking at the peak current again, so you can see there is that scatter of data, but even so, we've got reasonably reproducible EC50 data from this, which is in line with the published data. And then for 3 agonists, so isogerbin, muscarinic, and GABA, the data correlated very well with the QPAX data that we were also able to generate through colleagues at our site in the US. For positive modulators, you can see that we, for diazepam and pentobarbital, we also see reasonable potentiation, although the diazepam response is relatively small. You can see it gives quite a nice dose response. And again, the EC50s here are pretty much in line with what we'd expect from literature data. Going on to antagonists, then we were able to do a single experiment to generate some shield plot data to look at competitive and non-competitive antagonists. So just on the top left here, you can see the dose response for bicuculin, which looks good, and we're getting an IC50, which is consistent with literature. Again, for picrotoxin on the top right, you can see that as we carry out a GABA dose response curve in the presence of increasing concentrations of picrotoxin, we get a depression of the peak at the highest concentrations of GABA, which is what you'd expect for a non-competitive antagonist. And then for bicuculin, you can see that as we increase the concentration of bicuculin, the GABA dose response shifts rightwards the higher bicuculin you have in the well. So that's consistent with a competitive antagonist, and then you can carry it to a shield regression plot, and that gives us a slope of about 1 and a PA2 of 5.84, which is consistent with competitive antagonism. So then we brought these assays into production. We went to 5-point concentration response curves. We basically running now 2 separate assays where we have agonist and antagonist as a dual addition assay. So we add the test compound first, record whether those show any agonist activity, and then we add an EC50 of GABA and measure the antagonist effect of the compound after 3 minutes. And the positive modulator is similar, except that instead of adding an EC80 of GABA, we add a EC20. And we've just got some representative data from a couple of papers here where we've show the agonist, the antagonist, and some positive modulator data in this assay. And we've now run this for the identification of any sort of GABA-mediated liability in hit and lead compounds early on in our drug discovery processes. So going on to the nicotinic alpha-1 receptor, so we have an alpha-1 beta-1 delta epsilon cell line. As you know, this receptor has a critical role in triggering muscle contraction, and agonists or antagonists can cause muscular side effects such as paralysis or spasms. So the data here just shows addition of acetylcholine at different concentrations to the cells, to different wells on the plate. You get nice responses. The mean peaks are a little bit more spread out here compared to the GABA data, so a little bit more heterogeneity. Even so, we can get agonist dose responses to acetylcholine and antagonist dose responses to pancuronium. And we're now working to sort of implement this as a hit triage assay for assessment of lead compounds. Again, this is a faster response than the GABA channel, so we expect that heterogeneity at the top concentrations might be due to the onset of compound onto the cells, and the rate of activation and inactivation. But despite that, we've been able to get some good pharmacology from this assay, which is irrespective of the addition rate of the ligand onto the cells. Okay, I'll just pause for a moment and just to highlight that as for Ironworks Quattro assays, the quality of the reagents that we're using are important for these assays. For our GABA alpha-1, beta-3, gamma-2 BACMAM cell prep, we found that optimizing the cell plating schedule for our BACMAM transduction was quite key to getting good performance in this assay. So we were getting maximum currents of sort of 2.5 nanoamps using this system, but we noticed that we were only getting those on a Tuesday and a Wednesday. And when we looked at the cells prepared on another occasion and used on Thursday and Friday, we saw a drop-off in the current amplitudes. And what we realized was that it's basically how the cells are prepared prior to the BACMAM viruses being added to the cells that seem to be important. So cells which are set up on Friday, grown over the weekend, and then inoculated with BACMAM virus on a Monday, worked really well on Tuesday and Wednesday. But if we set up cells on a Monday and added BACMAM virus on a Wednesday, so 1 day less incubation prior to BACMAM addition, we then saw a complete drop-off in currents. And that's been a consistent finding from a couple of experiments. The other thing that was important with our nicotinic alpha 1 cell line here, I should say that we've previously been running a flipper assay to identify compounds that had liabilities at this channel, but unfortunately that was very poorly predicted, and we were getting a lot of false positives to the extent that the data wasn't really being used. Hence, moving it onto the Barracuda platform has helped with that. So we are currently optimizing that. But we found that the cell line that worked well in the plate-based assay needed some further optimization to give a good cell line. So we basically subcloned the cell line, and you can see we've looked at the control is the starting cell line in dark red. We've got 6 clones here, and the one in blue is the one we then went on and selected because it gave the best currents and best performance on the Ironworks Barracuda. Okay, so In my last few minutes, I'll just go on to describe a couple of other pieces of work we've done with other ion channels that we have reasonably good reagents for. So we've looked at transient receptor potential channels, TRPV1 and TRPV4. As you know, TRPV1 is expressed in sensory neurons, likely to be involved in nociception. It's activated by heat and chemical ligands, whereas TRPV4 is expressed in lung epithelia, and it has a role in maintaining cellular volume. It's activated by mechanical stimuli and chemical ligands. Again, we're using a Batman virus transduction system into HEC293s here. Show some representative currents. These are slower activating channels, so the time courses here are much longer. So the sensitivity to the ligand addition is less prominent here, and we can see a reasonably nice tight distribution of current in both cases. So just showing a representative dose response here, you can still see a bit of scatter at the top of the curves here, but we're getting a good agonist potencies for both of these channels. And just correlating some of the data we've got for antagonists in both of these assays to previous assay formats. So we were able to generate some data with TRPV1 on our Quattro platform using the techniques I described for GABAA. And we've got reasonable correlation here. And then looking at the Barracuda compared to a Flipper assay, again, a reasonable correlation, R squared of 0.9 and 0.8 for the correlation to the Quattro data. And then likewise for the TRPV4 data, it's a reasonable correlation. It's not quite as good, 0.7. And we do seem to have a ceiling of efficacy on the Barracuda here, and whether that's real or not, we're not sure. We think that we're limited in the compounds that we have really to dissect that further. So it'll be interesting to see if that's the case, if we do get more potent compounds there. More recently, we've also done some work with a pH-gated channel. Again, this is a Batman virus system in transducing CHO cells. Looking at pH-mediated activation, we get a nice current. This is, again, a bit more of a transient current. We get good mean peak current, so 3.2 nanoamps. Again, if we look at the current during the desensitization phase of that current, we get tighter data, so out to 2.5 seconds. You can see how on the histogram in blue that the distribution of the current is much tighter. But despite that, we can see good, use the peak current to derive reasonably good dose response curves from two tool compound antagonists. Although there's greater heterogeneity in the peak current for this desensitizing current, the antagonist pharmacology is reasonably reproducible. Okay, so then just to summarise our findings so far here, is that we have obviously good confidence in the utility of the Ironworks Barracuda to enable early hit triage for safety liability targets, including now a couple of ligand-gated channels. And the compound pharmacology we can generate for hit to lead and lead optimization is also looking promising, although I would say we've yet to really do that in anger for any channel at the moment. There's a requirement for robust cellular reagents. Moderate heterogeneity can be tolerated in PPC recordings, but it does depend on the desired output for assay. So using an assay for hit triage where you're looking for a liability against a ligand-gated receptor, we're confident we can identify hits that then could be progressed to other platforms. We haven't really done a SAR structure activity relationship campaign to drive lead optimization using the system yet. And so that remains to be tested in our hands at the moment. And we believe that the kinetics of ligand addition is likely to contribute to the heterogeneity. And although we see more heterogeneity, we're confident that we can use the system to generate reasonable data. There is the potential to use the Ironworks Barracuda for more compound mode of action studies on ligand-gated channels, because you could use the more detailed voltage, the more flexible voltage protocols to generate some detailed sort of voltage-dependent data for some of the ligand-gated channels as well. But we haven't done that yet. Something we'd like to move on to do. And we also haven't tried any of the very fast desensitizing, activating and desensitizing ligand-gated channels as yet, like P2X1 or Alpha 7. But that's something we may come on to in due course. I'll just finish by acknowledging the people who have really done the work here. So Kelly, Metal, Dave, and David have generated most of the data with the aid of a couple of students, Brett and Michelle. Stephen's been involved in data analysis and has really sort of promoted the use of the system for safety profiling. Rob and Muha have provided reagents and scaled them up. Brian, Chris and Tanya in GSK in upper Providence have provided Q-Batch data and supported us in that role. Claire, Dan, Tony did some of the early work on, developed the assay for the HERG that I mentioned, and also did some of the early work on the GABAA receptor, along with Craig, who's now with MDC. And just to acknowledge Jay and Mark from Molecular Devices, and more recently Mark Pate, who has given us technical support. Okay, so I'll finish there, and back to Jim.
Okay, thank you, Andy, for sharing your group's very nice work on the Ironworks Barracuda. It's also nice to see a little bit of Quattro data thrown in there as well. We're going to go ahead and wait till the end of the second talk for the question and answer session. I also meant to mention, please submit your questions by the Q&A tab in the WebEx panel. We'll, at the end of the second talk, or I should say after the end of the Q&A session, we'll leave the line open so that you can submit additional questions. And with that, we'll go ahead and turn it over to Mike. So, Mike, are you ready there? I see you're muted, so you're unmuted now. Okay, so I'll hand it over to you, Mike. Rim, I'm having some trouble passing it over to Mike. Can you do that for me, please? Thank you. Mike, you should be ready to go. I'll let you know when I can see your slide. Okay, it's coming up. Okay, there it is. All right,
you can see it? Okay.
Yep. Thanks, Mike.
All right. So good morning. I just want to start off by thanking Jim and Molecular Devices for the opportunity to come and present some new and exciting data that we've generated here at Europein. And so my talk is going to be looking at some GABAA validation data on the IonFlux HT. So Europein is a leading partner for the pharmaceutical industry with over 190 labs in 36 countries. Europein's Discovery Services, previously the Discovery and Development Solutions Unit of EMD Millipore, was acquired by Europein in April of this year. The Cell-Based Assay Services Group within the Discovery Services Unit is based in St. Charles, Missouri, which is approximately 25 miles to the west of the city of St. Louis. Europein's Discovery Services has an array of cell-based assay capabilities encompassing both products and services. On the product side, we currently have a library of over 60 precision ion channel cell lines and over 185 calcium optimized cell lines. Our service offerings are extensive and cover a wide range of screening platforms, from a basic ion channel profiler assay service to many custom solutions. We can meet all of your cell-based needs. Today my talk will center around the validation of ion channel cell lines that we've developed here at Europein. I'm sure the dendrogram of the ion channel superfamily is familiar to many of you. And I just want to use it to inform you that Europein offers precision ion cell lines in the highlighted channel families. And today, my talk will center around the GABA family. So I will start with some background information regarding GABAA ligand-gated channels, followed by a brief review of the ion flux, HT. I will then present some validation data for the different GABA receptor subtypes on the ion flux. And lastly, I'll compare the data generated on the ion flux with that from other competing automated electrophysiology platforms. So the next few slides are going to provide some background information on GABA receptors. Gamma-aminobutyric acid is the endogenous ligand for these receptors, each of which is composed of 5 subunits to form a central cation-permeable pore. Each subtype has a minimum of 2 alpha and 2 beta subunits, matched with a third, which for today's sake will be a gamma subunit. The GABA binding site is at the interface between the alpha and beta subunits, and its binding causes the channel to open, allowing chloride ions to enter the cell. This, in turn, stabilizes resting membrane potential, making it more difficult for excitatory neurotransmitters to generate action potentials. The effect tends to be inhibitory. As well, other ligands can bind to the GABA receptor, modulating the action of GABA in opening the channel. And there can be ligand specificity between the subtypes, and that is thought to be mediated by the alpha subunit. A good example of this is benzodiazepines, which bind the alpha and gamma subunits. They have different effects based upon which alpha subunit the receptor contains. For example, activity at the alpha-1 subunit is responsible for their sedative effects, while they're thought to affect their well-known anxiolytic properties via the alpha-2 and or alpha-3 subunits. And activity at the alpha-5 subunit is thought to affect cognition. It's important to point out that benzodiazepines do not bind at the alpha-4 and alpha-6 receptors, and this is due to a mutation in the alpha subunit that functionally abolishes the benzodiazepine site. So at Europein, we have recently expanded our range of ligand-gated ion channel cell lines expressing GABA subunits to include all 6 GABAA alpha subunits individually co-expressed with the beta-3 and gamma-2 subunits. And we run these cells on a regular basis, and this allows us to help troubleshoot your assays with our cells. We have offered GABA assay services for 7 years and counting here at Europein, and we offer a variety of platforms based on any throughput requirements. And these include ion flux HT, patch express, and manual patch clamp assays for agonist, antagonist, positive allosteric modulator, and positive allosteric modulator antagonist. And I also want to mention we offer agonist and antagonist assays on the iOS Quattro. So the ion flux is a high-throughput automated patch clamp system with the simplicity of a plate reader. And this is just to either refresh your memory or provide a brief introduction to the system as far as what it looks like and how the plates are laid out. Shown above here is the system, what the system looks like, and below is what an HT plate looks like, and it's essentially just an SDS 384-well plate with microfluidics stamped onto the bottom, and they are in these experimental patterns, one of which is highlighted in red, and there are 36 of them on one plate. 32, sorry. So each of those 32 experimental patterns is divided up into 12 wells, 8 of which can hold compounds. 2 are responsible for cell trapping, and the remaining 2 are responsible for the cell inlet and outlet, or waste. So what happens is the cells flow down this main flow channel and are pulled onto one of 2 cell trapping zones where up to 20 cells will be trapped and patched, and this can be seen in the picture below here. And then up to 8 compounds can be delivered to both of these traps, and this will generate up to an N of 8 in duplicate to give a higher data fidelity. So before we move on to the data, I just want to highlight a few key capabilities that make the ion flux ideal for ligand-gated assays. It's also extremely capable for voltage-gated assays, but that'll have to wait for another webinar. First, the microfluidics allow for continuous perfusion as well as rapid and precise delivery of test compounds. Also, the cells are constantly clamped for the duration of the protocol. And the other thing to mention is the assay time. It's approximately a quarter of an IronWorks Quattro or Patch Express run. And this not only means more throughput, but the cells will certainly be happier, and we all can appreciate that happier cells equals more robust data. So we have validated all 6 GABAA alpha subtypes co-expressed with the beta-3 and gamma-2 subunits on the ion flux using our Europein precision ion GABAA cell line. The experiments were run in ensemble mode with the cells clamped at minus 60 millivolts. And we looked at current stability over time in the form of a time-matched vehicle. Looked at inter-run variability by running the same experiment over multiple days and comparing the IC50 or EC50 values. And also generated data for reference pharmacology in agonist, antagonist, positive allosteric modulator, and positive allosteric modulator antagonist assays. So here's some data for the GABA alpha 1 and alpha 5 receptors looking at current stability over time. And what we see here are representative traces for each of the receptors from single cell trapping zones. And these are the corresponding long-term record trace charts for each of them. And what we're doing is just repetitively adding the same concentration of GABA to the cells. And it's pretty clear that the currents are stable, very stable for the duration of the experiment. And this is something that's really important for the development of any of the assay formats that I'll be showing data for. So one of which here is an agonist assay, and this is just looking at the agonist response on the GABA alpha 1 cell line. And so what we want to show is that these cells will respond to increasing concentrations of GABA in a dose-dependent manner. And the traces that you see here are, again, a representative from just a single cell trap. And they are exposed to increasing concentrations of GABA, starting at 0.1 micromolar, going up to 100 micromolar. And what we see is, if we, the red trace is the 0.1 micromolar GABA, and it's about 500 picoamps. And as we apply increasing concentrations of GABA, we see that the currents increase in a dose-dependent manner up to approximately 12 nanoamps with 100 micromolar GABA. And so we can fit this data to a curve and calculate EC50 values, and we've run this assay over the course of 3 separate days and calculated EC50 values for each day, and that data is shown in the table on the right. And what we see is that the data is very reproducible over the 3 days, and it's also in line with the manual patch clamp literature value. So we also looked at the other GABA cell lines and their response to GABA, and here's that data, and we can see a clear dose-dependent response to GABA for each of these cell lines. At the top are the curve fits, and the bottom is the corresponding data table with calculated EC50 values. We also compared the EC50 data for the GABAA alpha-1 cell line on the ion flux with that from other electrophysiology platforms. What we saw was that the GABA activity from the Europein precision GABAA1 cell line is robust and reproducible across multiple platforms, including the ion flux HT. So now let's take a look at some antagonist data for the GABAA alpha-1 receptor. And what we want to show here is that a reference antagonist will inhibit the current elicited by the EC80 concentration of GABA. And so the reference antagonist that we used was bicuculline, which is a nonspecific competitive antagonist. And again, the traces that you see here are the response of a single cell ensemble exposed to increasing concentrations of bicuculline, starting from 10 nanomolar going up to 100 micromolar. There's a 2-minute pre-incubation with bicuculline, followed by a 3-second application of the EC80 concentration of GABA. If we look at the traces, what we see is the red trace corresponds to the control current, or that elicited by the EC80 GABA alone, and it's approximately 12 nanoamps. And then as we apply increasing concentrations of bicuculline, we are able to increasingly inhibit that EC80 GABA current up to almost completely at 100 micromolar bicuculline. Again, we have a curve fit of the data showing a 5-point dose response. That's on the left. And again, as with the agonist assay, we've repeated this over 3 separate days and calculated IC50 values for each day. They are shown in the table on the right. And again, we can see that this assay is, the data is very reproducible over the 3 days of testing, and it's also very much in line with the manual patch clamp literature value. So here's the antagonist data for all 6 GABAA cell lines, and these data clearly demonstrate the ability to block the GABA current from all 6 of these cell lines in a dose-dependent manner with bicuculline. And again, at the top, you see the curve fit for all 6 GABA receptor cell lines. And at the bottom, you see the corresponding data table with calculated IC50 values. So benzodiazepines. They've been around for some time now and are well characterized. They bind to sites distinct from the GABA binding site, and they are responsible for allosteric modulation of the response to GABA and can functionally be either an agonist, antagonist, or inverse agonist. A key point to remember is that benzodiazepines have activity at all receptor subtypes with the exception of alpha-4 and alpha-6. So now we will look at the positive allosteric modulator response for the GABAA alpha-1 cell line. And what we want to show here is that the current elicited by the EC10 concentration of GABA can be positively modulated by diazepam in a dose-dependent manner. Once again, the traces that you see here are just from a single cell trap, and they're exposed to increasing concentrations of diazepam, starting from 1 nanomolar going up to 3 micromolar. And we have a 1-minute pre-incubation with the diazepam prior to a 3-second application of the EC10 concentration of GABA. And so if we take a closer look at the traces, the red trace corresponds to the current elicited by the EC10 GABA alone, and it's a little bit over 1 nanoamp. And then as we apply increasing concentrations of diazepam, we see that the GABA current is increasingly positively modulated in a dose-dependent manner up to approximately 4 nanoamps with 3 micromolar diazepam. So again, we fit this data to a curve, a 5-point, and we see a 5-point dose response showing a dose-dependent positive modulation of the EC10 GABA current. We've normalized the data to the control EC10 response and set that at 100%. And the highest concentration, 3 micromolar diazepam, gives a maximal potentiation of about 250%, or roughly 2.5-fold. Again, as with the other assays, we have repeated this on multiple days and calculated EC50 values for each day. That data is shown here in the table on the right. And again, we can see that the assay is very reproducible over the 3 days of testing and is also in line with the literature value. Here's the data for all 6 of the cell lines. And the data demonstrate the ability to positively modulate the GABA current in the alpha 1, 2, 3, and 5 cell lines, but not the alpha 4 and alpha 6 as we would expect. So, and again, the curve fits are on the top, and the corresponding data table with calculated EC50 values is on the bottom. So another assay that we took a look at is the PAM antagonist assay, and this can perhaps be also characterized as just a benzodiazepine antagonist, because you could look at it from the standpoint of a PAM response or a NAM or inverse agonist response. But in this case, we're just looking at the ability of a reference compound, flumazenil, to inhibit the GABA current that has been positively modulated by a maximal concentration of diazepam. Again, we have some representative traces from a single cell ensemble, and we expose this to increasing concentrations of flumazenil co-applied with the maximal concentration of diazepam, starting at 1 nanomolar going up to 10 micromolar of the flumazenil. And the flumazenil and diazepam are co-applied for approximately 1 minute prior to a 3-second application of the EC10 concentration of GABA. Looking at the traces, the red trace corresponds to the current elicited by the EC10 GABA alone, and it's about 1 nanoamp. And the orange trace corresponds to the positively modulated current as a result of the application of the maximal concentration of the diazepam, and that's about 3.5 nanoamps. And so that sort of defines the assay window And then as we apply increasing concentrations of the flumazenil, we can see that we're able to increasingly block that positively modulated response of the maximal concentration of diazepam all the way back to the baseline EC10 GABA response. And so this can be more clearly demonstrated looking at the curve fit shown here on the bottom left. And we have normalized this again to the EC10 GABA response and set that to 100%. The maximal diazepam response is shown by the dotted line, and that's approximately 300% or threefold. And then we see the 5-point dose response clearly shows a dose-dependent inhibition of the diazepam-potentiated current by the flumazenil. As with the other assays, we ran this one on 3 separate days and calculated IC50 values for each of those 3 days, and that is seen in this table on the right. And just as with the other assays, this one shows very good reproducibility over 3 days of testing. So I also want to show some PAM antagonist data that we generated for the GABA alpha 5 cell line. And the assay format for this is the same as with the GABA alpha 1 data that I just showed. And on the left, you can see the dose-response curve fit, again, a 5-point dose response. And again, the data is normalized to the GABA EC10 current, and that's shown by the dotted red line and set to 100%. The maximal potentiation with the Emax diazepam is this dotted line here, and it's approximately 200% or twofold. And then we can see a clear dose-dependent inhibition of that potentiation by the flumazenil, and we calculate an IC50 value of approximately 28 nanomolar. Then on the right, we have a time-matched diazepam control response. And I want to show this because this is really key to any successful PAM antagonist assay, and it's why it's so difficult to achieve this on other platforms, but it's yet one other strong attribute of the ion flux that we can achieve a very stable diazepam response over time. So the last thing we'll look at is the response of GABA receptors to barbiturates. Barbiturates are derived from barbituric acid, which was first synthesized in 1864. And they bind to sites on the GABA receptor, which are specific and distinct from the GABA site. They have 3 actions on GABA receptors: potentiation of the GABA response, direct activation of GABA receptors, and at high concentration, they can actually block the GABA channel. And they have activity at pretty much all GABA receptor subtypes, and this differs from benzodiazepines, and this is because the binding site does not involve the gamma subunit. So the reference compound that we looked at was phenobarbital, and we just looked at it on the GABA alpha 1 cell line. And what we want to show here is that we were able to pick up in this one assay 2 of those 3 barbiturate activities, one of which is positive modulation of the GABA EC10 current, and the other is direct agonism of the GABA channel. And so what we see here are, again, traces from a single cell ensemble. And the way that this assay is set up, the 5-point dose response spans 2 experimental patterns to do a a pre-incubation and then a co-application with the EC10 GABA. So these traces on the left are the three lower concentrations of phenobarbital. Here's the EC10 GABA alone. It's around little over 2 nanoamps, and then we can clearly see with increasing concentrations of phenobarbital that we're able to positively modulate that GABA current. Up here are the traces for the phenobarbital alone, and we can see at these three lower concentrations that we're not seeing any direct agonism of the GABA channel. But a little bit different story at the top two concentrations. Again, here's the current elicited by the EC10 GABA, and it's that 1.8 nanoamps. And then when we apply the top two concentrations of phenobarbital, 50 and 100 micromolar, we see strong potentiation of the GABA current. But we also see direct agonism of the GABA current with phenobarbital in absence of the EC10 concentration of GABA. And in fact, at 100 micromolar phenobarbital, the current elicited is actually larger than the EC10 GABA current. So here on the right, we have the curve fit of the positive modulation data, and again, normalized to the EC10 GABA, and it's set at 100%. And then we've calculated an EC50 value of 2.2 micromolar, which is in line with literature. And we have a maximal potentiation at 100 micromolar of approximately 300% or threefold. Looking at this bar chart here on the bottom right, we can visualize both the potentiation and direct agonism of the GABA alpha 1 channel by the phenobarbital. The blue corresponds to the potentiated currents, and the white would correspond to the direct agonism, just the phenobarbital alone. And so, again, we can clearly see direct activation of the channel at the top two concentrations and a nice dose-dependent potentiation of the GABA current as well. So in summary, we have demonstrated the effectiveness of the ion flux HT for detection of agonists, antagonists, positive allosteric modulators, and positive allosteric modulator antagonists of the human GABA-A channel. Pharmacological data from the 5 assays shown are consistent with the literature, and the calculated EC50 and IC50 values were consistent over 3 days of testing for the majority of the assays shown. And the GABA current, GABA elicited chloride current is very stable over time, which is very important. And the addition of the ion flux to our other platforms provides researchers in this field with another strong option to choose from to study these targets in depth. Now, I also want to mention that our validation efforts on the ion flux are ongoing. And in addition to these GABA assays, which we have now, which we are now offering as services, we have also, my colleague David Way has generated some nice data, which most of you have probably seen on our 5 nicotinic acetylcholine receptor cell lines, and those assays are as well available for service. And we've also generated some data on a few voltage-gated sodium channels, as well as a purinergic receptor, P2X7, and we will continue to validate other targets as well, and hopefully bring more and more online and available for service offerings in the near future. So with the addition of the ion flux, we at Europein now deliver fit-for-purpose GABA assays to our customers. And I just want to acknowledge the rest of the cell-based assay team here at Europein. and thank them for all their help and support. And I want to thank you for your time, and if anybody has any questions.
Okay, thank you, Mike. You and your colleagues are really generating all kinds of nice assays on your iFlux instrument. It's really nice to see. We're looking forward to more webinars from Europein, that's for sure.
Yeah.
So what we're going to do now is we're going to go ahead and go to the Q&A session, and Jeff Weber will be moderating that. So, Jeff, are you ready to take over that part?
Yeah, can you hear me?
Yes, I can hear you just fine. So,
okay, great.
Let me just briefly state, please continue to submit your questions by the Q&A tab or by the email address that's shown on my slide right now. We'll leave the line open after Jeff's done for about 10 minutes, and we'll continue to take your questions. And those questions that we don't answer live, we'll answer by email. So with that, Jeff, it's all yours.
Okay, excellent talk to both of you, Andy and Mike. The first two questions are going to be for Andy. So the first question is about your triage strategy in lead discovery. How does the Barracuda perform as compared to other ePhys platforms?
Hi. So we post HTS we haven't done that much as yet with the Barracuda, but for one of the ligand gated channels we are working with, we're just taking through hits from a screen at the moment, and we're showing that we're getting good correlation. So if we're doing replicate data on a single shot on different days, we get nice linear relationship, and the XE50s coming out of that are well correlated as well. And of course, we're comparing back to data from plate-based assay systems where you wouldn't necessarily expect that correlation to be entirely linear, but we are confirming a good number of the hits, and it's exciting times. We've got more work to do there, clearly, but it does fit in very nicely, and we're doing what we can do now on Barracuda really has enabled us from the point of view of progressing large ligand-gated ion channel screens.
Excellent. Okay, so the next question is, does the degree in heterogeneity seen in some assays at high agonist concentrations negatively influence agonist pharmacology?
Yes, I think there is a risk with that. I think it's understanding that heterogeneity, and if you're looking at generating SAR data for agonists, I think you need to be aware of how many replicate data points you need to generate to really strengthen your faith that you're reporting the right numbers back to the chemist. So there is that. Yeah, that we are aware of that, and it's something that we deal with by designing our strategies appropriately, I would say.
Okay. The next two questions are for Mike. The first question is, a stable diazepam response over time is difficult to achieve on many different platforms, and that's what makes an assay, PAM assay, challenging. How does the iFlux meet this challenge?
Thanks, Jeff. So the iFlux with the microfluidic system is very well equipped to handle an assay like this. The fast perfusion, as well as the unique ability or way in which compounds can be applied, really lends itself to generating a stable diazepam response. And so what I've done is sort of you can actually run two compound channels at the same time and actually layer one on top of the other, and then turn the sort of bottom one off, and the top one will just fall right onto the cells. So you get a very fast and very clean response. And so that's how what the strategy that I use, and that's something that just is very unique to the ion flux and a very strong attribute of the platform.
Okay, thank you. And last question, how does the ion flux complement your assay portfolio as a CRO and ion channel services?
So it fits in very nicely in between our IonWorks and our Patch Express and soon to be Q Patch. It's obviously not going to quite match the throughput of, say, an IonWorks in a screening mode, a single concentration. But in terms of doing the type of assays that, like I just showed, the GABAA assays, and generating those responses, it's going to have much better throughput than, say, the Patch Express. And even to an extent the Quattro and the time, just the fact that the experiments are so short, and so that increases the throughput, and so it's a very nice complement to the other platforms we have as well, for a number of the ligand gated and even the voltage gated channels that we've run. The data tends to be very comparable to manual patch clamp, and in some cases, we're actually able to do things on here that are difficult to do in manual patch clamp, specifically some of the ligand-gated and some of the nicotinic receptors. So, I mean, it's been a very good addition to our portfolio, and something that we're very, very excited to have. Okay.
Well, thank you again to both Andy Powell and Mike Donio for your time today. We'll be leaving please continue to submit your questions. We'll be, I believe, leaving this open for another few minutes for additional questions, and we'll respond via email to those questions.
Yep, that's correct. Thank you, Jeff. I'd also like to thank Andy and Mike for presenting today, and also to Jeff for the questions, and to all attendees. As Jeff mentioned, we will leave the line open for 10 minutes for questions, and we'll answer those that come in during that time by email. So thank you, everybody, and we're looking forward to presenting another webinar in the near future. Thank you very much.